Hello everyone, this is the part 2 video on laser production and laser properties. So for that I'm going to read Shield's textbook of glaucoma. It is the 6th edition, chapter 35 and page number 448. The introduction of laser, that is light amplification by stimulated emission of radiation therapy, was a significant advance in the surgical management of glaucoma during the second half of the 20th century. The concept of using light energy to alter the structure of intraocular tissues, however, actually preceded the development of laser technology. Mayer Schwickerath, I don't know the pronunciation, it's French name I guess. Mayer Schwickerath, beginning in the late 1940s, pioneered this field of ocular surgery, first using focused sunlight and later the xenon arc photocoagulator. Although the latter technique was useful for certain retinal disorders, xenon arc photocoagulation for the treatment of glaucoma never gained clinical acceptance. In 1960, Mayman described the first laser that used a ruby crystal stimulated by a flash lamp to emit red laser light at a wavelength of 694 nanometer. It was the development of the continuous wave argon laser near the end of the decade that brought on a virtual explosion of laser applications for ocular diseases. Since the first report of argon laser used for ocular disease in the late 1960s, numerous wavelengths arising from different energy-emitting sources have been tried. Lasers are now used to treat various forms of glaucoma, and today it is the most commonly used mode of glaucoma surgery. This chapter briefly reviews the physical and biological aspects of laser therapy. The application of these principles to the treatment of specific forms of glaucoma is considered in subsequent chapters. Basic principles of lasers. When the light is shined on a metal surface in a vacuum, it may free electrons from the surface. These electrons can be detected as a current flowing in the vacuum to an electrode. Only certain wavelengths can cause photoemission of electrons. In 1917, Albert Einstein wrote the quantum theory, the quantum theory of radiation, in which he speculated that light consists of photons, each with discrete quantum of energy proportional to its wavelength. For an electron to be freed from the metal surface, it would need a photon with enough energy to overcome the energy that bound it to the atom. His theory formed the basis of laser technology. When atoms absorb energy, called pumping, they are excited from a lower to a higher energy level. When a substance, for example gas, liquid or semiconducting material, is excited by energy, it emits light in all directions. The sources of energy used to excite the laser medium typically include electricity from a power supply or flash lamps, or the energy from another laser. If more atoms are in the excited state than in the unexcited state, population inversion is said to exist. Under such circumstances, photons with energy equal to the difference between the two levels of excitation have an enhanced probability of stimulating the atoms to decay back to their lower energy level by emitting photons, a process called stimulated emission. The emitted photons stimulate the emission of more photons, leading to a chain reaction. If the system is enclosed between two mirrors, the photons bounce back and forth, creating multiple stimulated emissions of light. A light amplification. So, stimulated emission means pumping of energy to the atoms to excite them, to excite the electrons from the lower energy state to the higher energy state. And then coming back from the higher energy state to the lower energy state and emitting photon, that is called as stimulated emission. And what is amplification? And these photons emitted, they excite the other electrons, and that causes a chain reaction. But these are not collimated, means they are not in the parallel directions. These photons, if we allow them to pass out of the tube, they are not collimated. Collimated means parallel to each other. So, and it is stimulated emission. It is not, this chain reaction is not called as amplification. Amplification is achieved with the use of two mirrors separated by the multiples of wavelengths of the laser that we desire to produce. So, if this system is enclosed between two mirrors, the photons bounce back and forth, creating multiple stimulated emissions of light or light amplification. The mirrors form an optical cavity which, in addition to amplifying the light, creates a parallel beam and acts as a resonator to limit the number of wavelengths. When the light amplification is sufficient, some photons are allowed to leave the cavity in the form of a laser beam to a partially permeable mirror. The laser beam can be delivered as a continuous wave or in a pulsed mode. In the latter situation, the energy is concentrated and delivered in a very short period of time, which can be accomplished in one of two ways. With one technique called Q switching, light is not allowed to travel back and forth in the cavity until maximum population inversion is reached. What is population inversion? Population inversion means more of the atoms or electrons or molecules are in excited state than in the ground state or the normal state. Ground state, you can say, a lower energy state. So that is population inversion. So Q switching. In this technique called as Q switching, light is not allowed to travel back and forth in the cavity until maximum population inversion is reached. This is accomplished with an electronic shutter or misalignment of the mirrors. When the shutter is opened or the mirrors are aligned, stimulated emission of light amplification occurs suddenly and the energy is released in a pulse of a few to tens of nanoseconds. In the other form of pulse delivery, called mode locking, the energy is also released after achieving maximum population inversion. The different modes of light are synchronized, creating peaks of energy, which are emitted in tens of nanoseconds as a chain of pulses, each of which lasts a few tens of picoseconds. To provide some appreciation for the gravity of these exposures, it has been noted that the ratio between the duration of a brief series of noise and a conventional continuous wave or one laser exposure is roughly the same as the ratio between the argon exposure and a human lifetime. Properties of a laser energy. Light emitted by a laser differs from normal white light in several ways: coherence, collimation, monochromacy, and high intensity. Coherence means all the particles in the same phase of oscillation. Collimation means parallel to each other. And monochromacy means same wavelength, same color. High intensity, the name itself means it has the high energy. So that was all about the laser production. In short, the properties of lasers. In short, I have not read the properties of laser because it is the same thing that I have said about it. And tomorrow I'm going to talk about the laser tissue interactions. So tomorrow I'm going to talk about the laser tissue interaction. For that I'm going to refer one book written by Bhattacharya. But that book, I don't know whether it's standard or not, but I like this book because it's a simple language and point-to-point notes. It's like a notes, but in detail, because it's specifically for the lasers in ophthalmology. So everything that an ophthalmologist requires to know about the lasers in ophthalmology, everything is given over there nicely. So I'm going to read that book. If some mistakes are there, because I think it is not standard book, if some mistakes are there, we are also referring the standard textbooks like Shields, then Jacobi's, then Elkington. So that's it. So tomorrow, laser tissue interactions from Bhattacharya. Then the day after tomorrow, laser tissue interactions from Shields, then from Clinical Optics by Elkington. Thank you so much for listening to me patiently. Bye. Take care.
Hi, I'm Paul from Physics High. Lasers. Now these are quite ubiquitous. That is, you can find them fairly cheaply these days, and you can use them to do all manner of things, such as pointed things, such as at my wedding ring. Lasers are quite common in industry and medical devices. They're used, for example, in eye surgery. They're used in industrial applications. And of course, every time you go to the supermarket and get your groceries scanned, they use lasers. But what makes a laser a laser? Let's turn the light off and examine the laser by using this deodorant spray. So what you notice is three things. First of all, it's monochromatic. That is, it only produces one color. Secondly, we have a beam that is coherent. That is, the waves that are coming out are all in phase with one another. And thirdly, we have what we call a collimated beam. That is a very nice focused beam. But why is it monochromatic? Why is it coherent? And why is it collimated? And what does laser actually stand for? Well, today I'm going to discuss the working principles behind a laser, so stay tuned. Now, laser stands for light amplification by the stimulated emission of radiation. Now, we're going to explore what that means, but we also want to address why it is monochromatic, coherent, and of course, collimated. So to start off with, we need to have a look at the structure of the atom, which is really about the substance that actually generates the photons that we want to have for the laser. Now, we have here the Bohr model of the atom, and I have a video that you can have a look at where I explore the Bohr model. Now, it is a simplistic model, and needless to say that the atom is far more complex, where the electron lives in probability clouds around the nucleus. But in this case, this model will suffice to help us understand what's going on, because the electrons do exist in what we call discrete orbits. They don't radiate energy in these orbits, and so they have various energy levels. And so my electron can exist in one energy level, it can exist in the other energy level, and there could be more further up. Each case, it is a step up in terms of its energy, but they are discrete energy levels or quantum energy levels. That means that the energy between one energy level and the other one is a very discrete amount. And this is where we're going to have an excitation going on here. So I will have a photon coming in, and if and only if that photon's energy is exactly equal to the difference between these two energy levels, that photon is absorbed by my electron, and as a result, my electron jumps an energy level, and so has a higher energy state. And then what happens almost immediately is that an electron jumps back to the lower energy level, what we refer to as the ground state. And so it drops down and therefore releases energy. But guess what? It releases the energy with exactly the same photon of energy being released. So that is under the principle of what we refer to as E is equal to hf, where f is the frequency of my photon, h is Planck's constant, and E, of course, is the energy. Now, that explains to us why it is monochromatic. As we'll see as we go on, all the photons we're going to be talking about are exactly the amount of energy that we are dealing here with their energy levels, and so therefore we will only produce photons of a very specific amount of energy, and hence it's monochromatic. Let's move on and let's look now a bit closer, because we've talked about emission, and in this case we've got spontaneous emission, photon coming in, electron getting excited, dropping back down, and then spontaneously emitting the same photon energy, but we want stimulated. And so what we could have is a situation like so. We have my electron here, and it of course is stimulated by my photon, comes in, of course my electron is absorbing that energy, jumps an energy level. Now, what if now, for example, while this electron is in this stimulated stage, what happens if it encounters another photon? And in this case, it absorbed that energy, but before it drops down, or whilst it drops down into its energy level, it now releases two photons. And so what we get here is an increase of photons, and so what we have here is an amplification. I started with one photon and end up with two photons. So in that sense, that explains the amplification process, though there's more to it, as you'll see. But the thing is that the second photon is exactly the same. So in other words, it is the same wavelength, the same phase, same everything. So we say it's coherent because they are in phase with each other. Now, why they are actually going to be exactly the same is actually a quantum phenomena that I'm not going to delve into now, and that could be something that you can look into further. But needless to say, we have now a duplication of our photon. And so that explains why it's coherent, because they are always going to be in phase. Every photon we're going to be producing will have exactly the same frequency and phase as a result. So I can have a photon going in and a single photon going out, which is spontaneous emission. I can have a photon going in, and if the electron is already in a stimulated stage, I can have two come out, and so now I've got stimulated emission. So what happens if those two photons encounter other stimulated electrons? Well, we start off with 2, of course, then we got 4, we have 8, then we have 16, and of course that continues on. And so what we get this cascade effect of all these photons being generated as long as they encounter stimulated electrons. But here is the problem. The time it takes for the photon to start in its excited state to back to ground state is very, very quick. So what is the probability that we have multiple atoms in their excited state? Well, really, really small. So small, in fact, that really this is not going to produce our cascading effect. And there's a problem right there, at least in the simplistic model. So we need to find a way of increasing the population of our excited state. And so what we get now is what we call population inversion. Let me explain what that means. So in this case, my population is in its ground state. Now I've got here 6 representative electrons in their ground state. And so the number of electrons in the excited state is going to be definitely different to the number of electrons in the ground state. So clearly our N2 is less than N1. If we want to have a continuing cascading effect, we need that to be reversed. We need more in the N2 state than the N1 state. And so what we want is what we refer to as a population inversion, because the population is inverted. We've got more in the excited state and less in the ground state. So how do we get them up there? Remember, as I said to you, that when they're actually pushed up there, they very quickly jump back. So even if we actually have a few stimulated before we have anyone encountering another electron, very quickly you'll find they will be jumping back down to their ground state. And as a result, the number N ends up being mostly in the ground state. So how do we solve that problem? Well, to solve the problem is by introducing a material that you can actually have a third level or a level 3 material. And so what we want to do is stimulate our electron beyond to the level that we want. And how do we do that? Well, we have here our second and now a third level. So imagine I fire a white light photon. Now you're going to say, hold on, a white light photon doesn't exist. You are correct. Actually what we have is, let's say, light that has basically white. So it has multiple photon wavelengths in there. And hopefully one of those photons, of course, will excite it up to this level right here. And so now what we have is our super excited electron. But the materials chosen here, that these two energy levels, or this energy level is very, very unstable. And so what happens is, as I pump the white light in, we have our electrons jumping up into this third level here, but very, very quickly it jumps down into this second level. And so what we now get is an electron that is in a second level that will stay there a little longer. Now this state here is referred to as the metastate. And the beauty about the metastate is that the time that the electron exists in the metastate is actually a little longer, up to 1,000 times longer than, let's say, in the normal situation. And so what that means is you're going to now get a situation where you're going to have a lot more electrons sitting in this metastate for a certain period of time, which means if I now have my photon coming in and it's experiencing an electron in that meta state, very quickly what we're going to get is that electron jumping down, and we now will produce 2 photons. It's more probabilistic for us to produce more photons that way. So in essence, what we get is this. So here is multitude atoms, and what we start to see in these electrons, and start to see in these atoms, we start to see pairs of photons coming off as they come out, and then of course they're interacting with other atoms as well. And then what you're going to get, of course, is an increasing or a cascading number of photons being generated in your material. But you can see a problem is that they're all going in different directions. We're not going to get, let's say, a strong focused beam. How do we do that? Well, the first thing we need to do is with our atom, as I said to you, is we need to apply some sort of energy source. Now, it can be a light source, but it can also be an electrical source as well. So this is what the stimulation aspect. So in this case, we're using light. And so there's our light aspect. We've talked already about the fact that it's amplified, and we've already talked about that it's by stimulated emission. So we've actually covered most of the terms already of the term laser. But what we want to do is increase the effect. So how do we do that? Now, the first thing we do is we add mirrors. What does that do? Well, we have, of course, photons going all different directions, but any photon that is going in, let's say, that direction is going to reflect back and go back in that direction. And then, of course, when it gets to the other side, it's going to reflect back in that direction and so forth. It's going to go backwards and forwards. And every single time you start to see a stimulated emission, you're getting more and more photons as it goes backwards and forwards and backwards and forwards. In essence, if we then look at the light in terms of its wave phenomena, what we end up setting up is a standing wave. It's actually what we call a resonance. And so what we get here is a huge amplification as we generate a standing wave of photons basically going backwards and forwards every single time, increasing exponentially as they encounter electrons. Now, at this stage, we've got it in a tube with two mirrors. But the beauty here, of course, is that along this path, it's very narrow. Anything that goes in the other direction will be bouncing off the mirror and goes out to the side, but we're going to definitely get an increasing effect along the line here perpendicular to our mirrors. Now, being a standing wave is that standing wave is determined by the wave formula, which is F is equal to NV over 2L, where N is basically equal to the different harmonics. In this case, I've got a harmonic of 2. The reality is that the harmonic we generate here is in the thousands. The frequency, of course, is the frequency of the photon, and the V, of course, is the speed of light, and the length is the length of the tube. So in other words, if you set the length of the tube right, you'll create the right resonance for the wavelength that you're interested in. And in this case, for example, a red wavelength, let's say 632.8 nanometers, which is the wavelength for a helium neon laser. So now that we have set up a standing wave, we need to now somehow let the light out. Well, I need to change the transparency of my mirror. Now, by changing the transparency of my mirror, usually only about 1%, so in other words, it's now 99% reflective, I'm going to get some of my light going out, and I have my laser beam. Because the light now is only what is going perpendicular to my mirror along that line, that central line, it now explains why we get a really tight beam, and it is collimated. And in some lasers, what they might also do is put a small lens to really adjust for any imperfections that may exist. So in summary, let's quickly review. What did we use to pump the energy into our tube? We used light. What did we end up getting? We ended up getting more photons, so we had amplification. How did we do that? Well, we had to have emission, but it had to occur with electrons that were already stimulated, so we had stimulated emission. And as a result, we get a nice monochromatic, coherent, collimated beam, which we can call radiation. Well, I hope that has helped you understand how a laser works. Please like, share, and subscribe, and put a comment down below if this has been helpful for you. And consider supporting me via Patreon. My name is Paul from Physics High. Take care, and bye for now.